I'm very happy to be invited to give a talk. And today I want to talk about StreamDiffusion, a pipeline level solution for real-time interactive generation. And last time I heard that Jeff has talked about StreamV2V, so I will make sure that you could learn something new from my talk. I will give some like shared technique, but I will also introduce some new technique we recently did. And yeah, thanks. Next slide. Okay, so this is the picture about the landscape of deep generative learning. So you could see that. So this figure is from UC Berkeley's Professor Chenfeng Malik, and you can see that there are lots of different deep generative model, like normalizing flow autoregressive models, and VAE and GAN. And you could see that the diffusion model is on the local minimum. So this figure want to like express that the diffusion model is different from the others. And you can see that diffusion model is a little bit lower than the other models. This means we are close to a local minimum. So what is diffusion model? Next slide. So diffusion model is very simple. It's nothing but just during training, given an image, you just add in the noise, and you will train a parameter to denoise it back from the pure noise into the image. So during inference, you will like also directly start from a noise and using this denoising model to generate the final image with some prompts. And next slides. And maybe like yeah. So yeah, okay, it's fine. So it's apparently that diffusion model is very slow because you have to denoise it step by step. And here's a comparison between the GAN, VAE, and diffusion model. You can see that diffusion model can generate the high quality samples, and the mode can coverage quite various diverse images. But the problem of the diffusion model compared to the other generative model like GAN and VAE is that it cannot achieve fast sampling. It's very slow. And next slide. And there are several like efforts like want to accelerate diffusion model. For example, the very common technique is try to reduce the denoising step, and one very representative work called LCM. So LCM is also a simple idea that is given a random noise. Like you can see, like you can look at beginning and the last image is random noise, and it denoise step by step. And during training, what they do is that we do not calculate loss at the last image. Instead, we calculate loss. We will generate the image from the middle stage, and we hope the middle stage generated image could be close to the final step, the generative image. So we want to make the distance close to each other. In that case, we could directly extract the middle stage generated image. This can help us to reduce the step. And next step, and then next page. And another kind of idea is the distillation method. So we could use a multi-step denoising model, diffusion model to distill a single step or two-step or several step diffusion model. So we can use this kind of distillation method to make few-step diffusion model achieve similar performance with the multiple time-step denoising model. And maybe click. Yeah. So, however, they have some problem that is we have to either do some training, we have to fine tuning, and if we do not have like high quality data, this kind of fine tuning or tuning will make performance not that well. And so do you have other? Yeah, no problem. So do you have other solution that's not hurt the performance? And now we want to do a living streaming application, and we want to, let's say like you want to broadcast the beautiful scenery in front of the house, but in a cartoon style. And basically we don't give you any training budget, and we don't have like training data. So we can just give you one pre-trained diffusion model weight. So how can you do it? And next slide. And StreamDiffusion provides you a solution. So we utilize a new pipeline level solution for the real-time interactive generation. In the stream diffusion, we have a bunch of technique composed to each other. And let me introduce it. Let me introduce several key components for you. So first, next slide, is stream batch. Okay. Next slide. So yeah, so the conventional method to generate the image is very it's very exhausting. So the conventional way is given, like, let's say that we have streaming image comes in, and we do it like image by image. We have to like denote each image first, and then the next image, like image by image. So it's too slow. So do you have a way to accelerate a little bit more and click? Yeah, so we introduced the stream batch. So you can see, given the streaming image, like when the first image is denoising, the second image is already comes in, and we can take it, and then we can also batch them together, batchify them together, and we can denoise them together. So in that case, we could improve the throughput by a lot. And next slide. So you can see that without any performance loss, with our batch-based method compared to the normal or conventional method, we can improve the throughput by 1.75 in average for different denoising models. So you can choose your own diffusion model with either 20 step or 4 step or 10 step. Anyway, we can improve it by like steadily by like 1.75 throughputs in average. Okay, next slide. Yeah, and stream batch also provides us a bonus. The bonus is that you can see that stream batch can denoising the image through a batch for the different like streaming inputs. That means we could share the information together. And in Jeff's talk, he mentioned about one technique called the feature bank. Actually, the feature bank is try to interact the information from the given the current image, we want to get information from the passing image, and we can share this information. And in our stream batch, we try to incorporate the future information. So you can see that you can see the IT you can see the IT plus one row. The second row information is passing to the IT row. So I would not say that which one is better, mine stream diffusion or Jeff's stream V2V. So we find his performance actually is better, but I only say that he puts he shared the information from passing image, and we share the information from the future image, and all techniques can be combined to each other. And we are currently collaborating to incorporate his feature bank with our future image. So this and okay, next slide. And we conduct a brain study for it. The first row is the source image, is the input image, and the second row is without any cross attention or like future information sharing technique. And third row is ours. So you can see that if you look at the third column and the fourth column, the style of the image is different. So for the second row, the style of the image is different from the others. But with our future information sharing technique, that the style is more consistent. So note that this is also training free technique. We don't have to do any training, so we can improve it, and we can improve the consistency like a little bit. Yeah. Okay, next slide. Okay, the next technique is the residue CFG. Let's okay. So before I introduce the residue CFG, I want to first talk about the classifier free guidance, or CFG. The CFG is okay. So let's generate one image with some prompt, and our goal is to generate the random noise we call XT, and we want to generate X0 on the left corner. And next slide. Okay, the first step is that we want to predict the X0 heads. The X0 head, what that means? It means that we want to generate noise in an unconditional way. And next step. And next we want to predict X0 heads condition on Y. And Y is a condition. This is noise with this is noise represent the condition term. And next slide. Yeah, and then we calculate the difference between the condition term and unconditioned term. And next slide. and we scale it. We scale it with some like guidance scale factor, and with this guidance factor, we want to update the xt. Oh, next slide. Yeah, so this is the classifier-free guidance. And next slide. So apparently that you can notice, always we have, so for each step, we have to calculate the x hats twice. So one is for unconditional term, and another one is for the conditional term. So this is this so this computation cost is at least like 2 times than just you denoise 1 times. So we want to reduce it, and we can dive into a little bit what is the unconditional term means. So the unconditional term means that the diffusion model want to like make the noise image direct or step directing to the distribution of the training data set. So why we have to do that? Because in the CFG that we don't want to the generated image bias to some random distribution, because diffusion model is trained on some training set. We hope that the generated image is similar to some training set. We don't want to bias to some random style. So in CFG, we will always predict the unconditional term to make it as a center, and we calculate the distance between the conditional term and the unconditional term to update the unconditional term a little bit. So this is the principle of the CFG. However, in our case, because we are doing a streaming case, we also have some input image. That means we already provide some centers for the image generation. This center is exactly our input image. And next slide. So here we introduce the residue CFG. So we can refer to the initial image more. We can directly use this our initial image or input image as the center of the generated image. So in the diffusion model, we could control this by create a noise tracker between the input image, original input image, here is x0 to the x capital T. So we can directly draw a noise trajectory between them. In that case, we don't have to predict the unconditional term step by step. So this is our core idea. And how to draw it, this noise tracker? We can use some noise schedule, like a linear noise schedule. We can also use nonlinear, any schedule you can use. You just draw a noise tracker between the x0 and xt. So we can use this noise tracker to replace the unconditional diffusion unconditional term from diffusion model. So this could help us to save one more computation during each tuning step. And next step. So you can see that we can, by utilize this technique, we can achieve up to around like 2 times throughput improvement. And here is, if you look at the like the 1, 2, 3, the third column, here is a one time negative RCFG. That means that we still use we still predict the unconditional term the first step, but for the other step we do not predict it. So we find so this is slower, a little bit slower, but the performance is a little bit better. So we have already like all of the other denoise step for unconditional term, but we just predict one time at the initial step. And the second column shows that we do not predict any unconditional term. We directly use the trajectory between x0 to the x capital T. Okay, next slide. So here is our like visualization study. So you can see that with our RCFG like self-negative means that we do not predict any unconditional term, and one-time negative means that we predict one unconditional term during step. So you can see that the prompt is white tiger. I think I would like I'm more like our generated image, and you can see that the second row is red painting nose, white painting face, joker, and horror. So basically, I think our negative, self-negative, and one-time negative RCFG highlights more about the prompts because we have white painting face, but the others does not have highlighted too much. Okay, next slide. Okay, so the RCFG and stream batch is our key technique. I would say this is a algorithm level like new like contribution or innovation. And we also have some engineering, engineering contribution, for example, like the stochastic similarity filter. So during when we're like doing the streaming application, the streaming inputs comes in, and we find that for a lot of cases that for example, when Eric is streaming and he want to get coffee and he leaves, but he forget to close the camera, and we don't want to the model or like continue to like calculate or do some computation because it costs a lot of energy. And our solution is very similar. We will calculate the similarity between frame by frame, and if the image is very similar to each other, then we will not run the UNet to conduct the generation. So this could help us to save a lot of energy. Let's say next slide. So you can see that here's an example that so the up row is our input image, and the second image shows that our average skip probability. That so basically the higher means that we want to skip it, and the lower the bottom image shows that the energy use. So you can see that the yellow line shows without any of our stochastic filter. So you can see it keeps like cost the energy, and the blue line shows with our filter that we can save the energy a little bit a lot, and we calculate the average energy reduction is around 2 times reduction. So I think this could be very helpful for us. Yeah. And next slide. Oh, and we also conduct the user study. So this user study is about so the first row, the first row and the second row shows that with and without future framing like injection. And you can see we conduct user study for like 486 people, and almost all of them like our future frame injection technique. And you can see SSF. So SSF is the energy reduction user study. You can see with our stochastic like filtering that even like uses more heat, because first we save energy for them, and second that we can even like mix the like let's say we from the statistic like very static like image to a very dynamic image. This transition would be very hard for the diffusion mode, and with our SSF we kind of smooth it, so we make it more smoother. And we also conduct like a brief study for the hard threshold and our like SSF threshold. This is a two like technical detail. That means we could either use a hard threshold. For example, we calculate the similarity between one image and another image, and if the similarity is higher than one threshold, then we pass it. Otherwise, we like skip it. So basically in our method, we did not do so. We try to calculate probability. We use a probability function. We input this similarity into probability function. We would make it like a little bit softer. That helps us to ensure that we don't skip it hardly. We skip it in a smoother way. And from the US study, we find that our smoother way is much better than the hard way. So next slide. Okay. Oh, maybe it's like previous slide. Okay. Yeah, and now I want to introduce something new that this is our recent efforts. For this, so currently, like in our StreamDiffusion, we use the image-based model, like diffusion model or stable diffusion v1.5 and LCM. All of them are the image-based model, and currently, like video-based model are very popular, and their performance is very good. And could we like replace this image model with the video diffusion model? And yeah, this is what we are currently working on, and I'm excited to I feel very excited to share it first. And so now we extend StreamDiffusion to video generative model, but what's the what difficulty we face if we want to use the video training model? Of course, it's even slower. It is even slower than image-based model. And we find, so we analysis which part is the slowest part. And you can see that we find that at attention, the attention map part is the main computation bottleneck, because attention map is the complexity is quadratic to the context length. You can see when the context length becomes longer, the computation cost from the attention map gradually dominates the whole computation cost. And the context length becomes longer means that we want to use the larger resolution, or we want to use the like larger sequence of the videos. So you can see the attention map like is the main computation bottleneck. And next slide. Yeah, and even though the calculated attention is the bottleneck, and we can find some information from the attention map to help us extract it. That is, we find the attention map present two kind of patterns. The first pattern we call the intro frame we call it kind of diagonal pattern, or it's like an arrow shape. So basically, you could see that the first row is like a diagonal, and actually there are two lines on the there's two lines on the first column and the first row. So if we extract it, it's more like arrow. So we call the arrow shape. And the second kind of pattern is we call the zebra pattern. It's just like stripe, like zebra stripe pattern. So why do we have this pattern? So for the first row, you can see if we actually this pattern is like if you can zoom it up, I don't put it. I don't put it in the image. If you can like zoom it, and we would see that this kind of pattern is conformed by some like block. Each block means one frame, and we can see that we could see that actually in the attention, the token from the same frame would always attend to the same frame. So this is why they have this kind of diagonal pattern. And for the second row, that's why we have the zebra stripe pattern. This means that the token from the first this one like that's the first token in the first frame. It will always attend to the first frame from the second frame. The first token from the first frame would always attend to the first token from the second frame, and like do it like again and again. So this why do we want this? Because this can ensure that the video has very good smoothness. So we find that almost all of video diffusion mode has this kind of attention pattern. And if it presents this kind of diagonal pattern, it's very easy for us to accelerate it, because we only calculate the attention from the diagonal part. We can use one technique called the block sparsity attention, and this is one technique from the OpenAI. We can accelerate diffusion model by a lot. And if it presents the diagonal pattern, the zebra stripe pattern, we don't want it because it is incompatible with the block sparsity. It will waste a lot of compute. Yeah, in that case, we could rearrange the frame tokens to make it like present this kind of diagonal like block pattern. In that case, we can make it compatible with the block sparsity, and it's good for us because we can conduct the efficient calculation. And we found that you can like by combining these two techniques. The two techniques means that we can like utilize the block. We can utilize the diagonal pattern for the block sparsity. We can also use real order plus the diagonal sparsity. By combining them together, like we can accelerate 3.3 times throughput improvement. And next slide. Yeah, and recently we conduct experiments on the Quark Video X, and you can see that the dense attention means the original model. We do not change anything, and ours means that use our technique. We find that with our attention technique, we can accelerate by like 3.3 times, like from previous 10 minutes to generate one video. We can just use 3 minutes to generate one video. And I know that so basically we for this throughput, I don't think it's still enough for the streaming application. And now we are doing quantization and plus some like distillation method to make it faster. And after we finish this part, I'm very excited to also incorporate this technique into StreamDiffusion and help like Livepeer colleagues like to like have a better model. Yeah. So yeah. So this is our so basically this is our original. And next slide. Yeah. Maybe you can click twice. Yeah, I just show some. Here I show the StreamDiffusion demo. I think many of you have already saw it before. So basically, by using the iPad on the left side, and we just do some sketch, and you can see we can generate some very beautiful image from this sketch. And next slide. Yeah, and then maybe you can just click. Yeah, okay. Oh, sorry. Could you like go back to the? Oh yeah. Okay, next. Yeah. So basically, there are lots of demo from the like StreamDiffusion community on Twitter, and for example, like for the left top part, some users use our StreamDiffusion and try to visualize the music. So you can see like by play the music, our StreamDiffusion can generate very like flowing image to visualize it, and you can also see that the middle bottom part that we can use the button to control the generated image smoothly. Yeah, and the right image shows that this is from a pattern from A6Z. She used our StreamDiffusion to make make their home as better like background. And yeah, so next slide. Yeah. So besides the efficiency, I'm very proud to tell you that StreamDiffusion also enables something previously impossible beyond the efficiency. For example, the chief of the innovation at DBT Studio, he used the visible lights. He want to use our StreamDiffusion to generate some art image, and he used the visible light. You can see he just play this visible light, and StreamDiffusion transform it into very beautiful flower image. So you can see this is very, very cool. And next. Yeah, and another very popular demo is that is from Hirokazu. Actually, graphic people. So a lot of researchers from graphic people, from graphic fields, told me that they are very exciting because this is a potentially new paradigm for the graphics. Because in the graphics, if you want to like render high quality fluid, the cost is very high. It's very slow. By now, StreamDiffusion provides a new possibility for them. That is, they can use the low quality render. It's very fast, and plus our StreamDiffusion, and to transform into a higher quality. So this is something new. Like even graphic people really like it. And yeah, next slide. Yeah, and besides the like visual part, and actually StreamDiffusion can also extend to the robotics part, because like I and Akil's lab are also working on some robotics. So it's very natural to think that how we can use StreamDiffusion help the robotics field. And in robotics, that collecting the robot data is very exhausting because we have to control the robot, use our hand to control the robot to put something or like open something. It's very, very tired for us to like collect a lot of data. However, if we have StreamDiffusion, we don't have to, for example, collect. So if we can just collect one kind of robot data, and we can directly transfer it to another kind of robot. This helps us to reduce the efforts of robot data collection, and this will also get accepted by Coral as a oral presentation. So yes, so this is some extension for StreamDiffusion, and I think that's all 5 slides. Yeah, thank you.
Cool. Well, thank you, Chenfeng. This is really cool. We have a couple minutes left here. I unfortunately have to jump at the top of the hour, but I think there are folks who have a bunch of questions. I don't know if Rick or Prakash or Ryan, you guys will be able to stay a little longer to have a discussion. And also Chenfeng, how's your time doing?
Sure, sure.
You can stay a couple minutes
Yeah,
over.
I can stay here. Yeah.
Okay. Rick,
One,
Prakash, and Ryan.
one note from me before we start. So if there's any questions in the Discord, I'll communicate those here. So I'm just gonna ask folks in the Discord if they have questions too.
Okay.
Oh yeah, good idea.
Yeah, great. Can you hear me? I'm now here.
Yeah.
Great. So thank you so much for this amazing talk. It was nice to see the research and really dive into the research, understand what it does, and also it's very inspiring to see what your team has created in this domain. So we are really excited to work with you and really excited to start working with you on integrated into Livepeer network. We already have our engineers have the StreamDiffusion working, but as you know, we're trying to now also get it to work in ComfyUI and really transfer it over to ensure it's in ComfyUI. So I had some questions. I know that Prakash, who joined us, our AI researcher, has questions, and also Ryan, who's also our engineer, has also some questions. So the questions from me are, I think, mainly so about the path that you're taking. So you created StreamDiffusion. To begin with your group, Jeff made Stream V2V with the feature map there, the temporal feature map to improve temporal consistency. And now you're working again on StreamDiffusion version 2, right? Where you, if I understand correctly, you're looking at the techniques that you already have and applying it on video.
You're right.
Video model. And so for the version 2, that will mainly be trying to get the video model as good enough to make it real time, right?
Right. Yes.
And then and for the image-based model, are you going to transfer back, for example, what Jeff did in Stream V2V, also in the StreamDiffusion model, the image-based model there?
What do you mean transfer back? So basically, even though we work on the video model, we will not like drop it. We can provide 2 different versions to the users. Yeah.
Oh, nice. Yeah, that was mainly the question there. So also from an engineering perspective, then what would be the best way to implement it? Would it be to go with StreamDiffusion version 1, what that's now very stable in a sense? Would it be better to use Stream V2V? That has the solved the temporal consistency problem there, but has a lower frames per second rate. And then later look at your StreamDiffusion version 2 with the video base to improve it based on that. So that was why I asked the question. So what would be the best step moving forward implemented in ComfyUI? And I think my engineers and also AI research have more questions about it.
Yeah, sure. So I would recommend that so basically Stream V2V is open source, so I think you can directly build upon that. And because Stream V2V you just it's nothing but okay, I cannot say that it's something that in combines StreamDiffusion plus his Jeff's feature bank technique. In that case, that you can directly use that. It has a better temporal consistency, and if you turn off the feature bank technique, then it's just StreamDiffusion. There's nothing changed. It's just StreamDiffusion. So you can direct start from that. And in the near future, that we will incorporate the video model into the StreamDiffusion. In that case, you just I think it's nothing but just replacing another kind of model. So I think that the workload would be not that heavy.
Yeah, thanks so much. I think then my understanding there is correct. So really, StreamDiffusion built on top with the temporal consistency solution is Stream V2V. The frames per second rate will lower,
yes,
because you need to go computational to process more.
Yeah.
And then later the version 2 model will really be meant on video to even improve this temporal consistency.
Right.
So I know that Prakash, I will get him the state. He has some questions on that as well.
Yeah. Hi, Chenfeng. How are you? That was a great, nice workshop talk. Thanks for it. Pretty nice. So I had some questions, regarding your StreamDiffusion, as well as as you're also the second author for Stream V2V as well. So my first question was just pretty simple. Like the paper for the benchmarking, they were circling for 92 FPS, right? Like the StreamDiffusion worked at 92 FPS, I guess. So was that the best, or like what was the optimization, or what were the parameters behind to achieve that benchmarking result of 92 FPS or 49 FPS?
You mean how could we achieve it?
Yeah. Basically, how can we as
Okay.
users achieve it?
So basically, when we achieve such a high speed, we incorporate lots of technique. First, that we use the LCM. So we use the LCM that is like just 4-step denoising model. So it's faster than like traditional stable diffusion with like 20 or 50 times denoising. And we also use some TensorRT, and with TensorRT could help us help us improve the throughputs freely without any performance hurt. And we also use some tiny autoencoder. So basically, we found tiny autoencoder is very important for the image generation speed. So it's also costs a lot of time. And if we combine with stream batch and RCFG and SSF, this technique, finally we can achieve. So 91 FPS is the best speed, or the best benchmark, the best score in the benchmark. However, if for our like common use that maybe we don't have to be such fast, we want like a little bit better performance. In that case, we could like do not use LCM. Instead, we can use the stable diffusion. Even it's slower, we find it can still achieve like around 40 FPS. So I think maybe it's already enough for streaming application. And so basically, so in as far as I know, the streaming V2V also use the stable diffusion instead of he has two versions, stable diffusion and the LCM version. So basically, with stable diffusion version, the performance is also much better, and it still keep a relatively high FPS for the streaming application. Yeah.
Yeah, and also like the optimization techniques were used in StreamDiffusion paper like RCFG, right? Is there any way to directly incorporate that technique in other image pipelines? Like, is it
Yeah.
possible with your
It is possible. Every optimization way to improve the latency of the stream diffusion is easy to implement. Yeah, we don't have very like complex technique.
Yeah, and also like in StreamDiffusion we use LCM, right, to decrease our de-noising steps from basically from 20-30 range to just 2 to 4 steps of de-noising, right? So did you also make some benchmarking study or other kind of ablation studies to incorporate other methods? For example, like you also mentioned distillation method, right, to decrease our de-noising step. So was there any research behind
Yeah,
this method?
good question. So no, we don't have a very strict benchmark to compare LCM distillation and so on. So because we provide, so at least from our stream diffusion, like aside that we give users a pipeline. So in this pipeline, you can utilize any other model. You can also use distillation method or some method in like plus our stream diffusion. So we don't have some we're orthogonal, so it's hard to like compare them. So because we are orthogonal, so it's hard to compare with. We can integrate them, so it's hard to compare directly. Yeah.
And just a few more questions. So like there's some other models as well, like
Prakash,
for example,
quick thing.
SDX.
Can we do an audience question and then go back to one of your questions?
Sure.
So we have Define in the Discord asking this. Do you think that the workflow will overcome completely the image-to-image workflows when real-time video model workflows happen? And there's a second part to it. Or do you think that image-to-image workflows will continue offering superior quality for real-time streaming applications in comparison to real-time video workflows?
Yeah, so good question. So basically, it's a very good question. So whether we want to choose the image-based workflow, video-based workflow. So at least from the quality, video-based workflow quality, the quality of from the video model, the temporal consistency is much higher than image-based model. But we find the image-based model is more flexible because there are a lot of open source image-based model that the quality is higher and higher. For example, like, and it also becomes faster and faster, like Sana, like Flux, and this kind of model. They have very good quality and very fast. And we can also use like a lot of different prompt to control like audio and even text. So the flexibility is also higher than video-based model. So I think in the short term, that image-based model can still be better for streaming application because you can have a different way to control it. And for the video-based model, I think the benefit is it really has good temporal consistency. And but it's currently slow and currently we only have text prompt to control it. So so basically the flexibility is a little bit like worse than image-based model. And on the other hand, that video-based model has very few open source model. We only have like Hunyuan, Quark Video X, and like OpenSora. This like 3 very popular model we can use. And for the others, like the quality is not as high as than the Quark Video X. Yeah. Yeah.
Awesome, thank you.
Hi, Cheng.
Hello.
I have a question. So when you talk about, video models,
Mhm.
they don't really make sense in the real-time use case, right? Because, video models definitely you'll have to send a video and not an image, so that adds a delay. So it might not really make sense in real-time use case, right? I mean, if you have to compare between image workflows and video workflows, what would the delay difference be in terms of latency?
Yeah, good question. So basically, video model can, so basically, we are currently accelerate. We hope the latency could be definitely would not be as fast as the image-based model, but we're currently trying to improve the throughput into like I think I'm not sure whether 10 FPS is enough, but let's say if we can like X-ray diffusion model like by 10 FPS, I think we can still use it. We can definitely use it for the streaming. So, but currently it's too slow. Indeed, it's too slow. So for the current stage, it's nonsense to use it for the streaming. Yeah.
But what I mean is there will be delay in terms of input and output frame, right? Because video, you probably have to batch it together into like a 1 second or like 2 second video and then send it, right? So that way.
Yeah, we can control the input and output like batch like or slide window. Let's say that we can previously we are transfer one image to another image for image-based model, but for video-based model we can transfer a bunch of like frame to another bunch of frame, and we could use slide window to control the output streaming. We can also use some like hour control to make it smooth. Yeah.
But what is the smallest size? I mean, what are the smallest number of frames that you can send to the video model?
Yeah, let's say for example like 10 FPS. So we can every time we can just send 10 images into the video model and output another 10 image.
Got it. Thank you.
So are you already at that stage that you're at 10 FPS or not yet?
No, we're not. Yeah.
No, I saw the 3 minutes for computation, but that
Yeah.
core stage work.
Yeah. Yeah, we are working hard to want to achieve it as 10 FPS as fast.
Yeah, just one question regarding the RCFG usage for optimization. Like, were there any drop in quality for skipping the unit inference with RCFG?
Yeah, good question. So basically, we calculate the clip score. We also conduct user study. Basically, even some user like our RCFG, and for clip score, we also find that we don't drop a lot in like very similar clip score to previous FG.
Yeah, and just one last question regarding the StreamDiffusion version 2, which we were talking about on the video-to-video model. Like you mentioned, like that because of the huge computational overhead due to attention now.
Right.
Right? Can I guess like I read the paper in which they were using, I guess, mask guided sparse transformer, like basically masking the image frames and also using sparse attention, like basically it was called as mask guided sparse transformer.
Right.
So can we use that architecture to solve the compression overhead for attention?
Right. So basically, we definitely can utilize some sparse attention or linearized attention to accelerate. But basically, for this so basically for this kind of method, they have to do some fine tuning. Otherwise, but given a pre-trained clock video X, we don't have training budget to train it. So our method is a training free method. Given a like video model, we can direct accelerate without any training.
Just one last question. For combining the feature bank, the feature bank which is used in StreamDiffusion and the one you mentioned in StreamDiffusion, which we use plus one, like the future frames. Can we integrate both of these, techniques to make them better target?
Yeah. So we are working on that. So yeah, we are currently like feature bank is for path frame to integrate path frame information. Ours future frame. So we can definitely combine them together. Yeah.
Great. That was it.
Nice.
Okay.
Ryan, do we still have some questions? I think the implementation steps are quite clear here, but I'm wondering if you have some questions.
Yeah, it seems pretty clear to me, and Prakash actually asked most of my questions. So the 90 FPS claim that was with LCM.
Right.
Is there an advantage of LCM over turbo?
Is there an advantage of LCM over turbo? So basically, when we implement this, LCM is easier to implement. For turbo, I don't think we have a version for turbo. But it's possible that we can use turbo. Yeah, but yeah, we don't have this kind of implementation so far.
And have you tried? I saw that you did your experiment with Cog Video. Are there other models that you're experimenting with as well?
We also did experiments on Hunyuan. From it's also like Chinese video generation model. Yeah, from Tencent.
Cool.
Yeah, if I'm not wrong, I guess in StreamDiffusion as well as in StreamV2V, you guys are utilizing LoRa to add the weights to the StreamDiffusion model. Basically, I also tried using S3 Turbo in StreamV2V as well. So I guess in both of the pipelines we are utilizing LoRa, right? So it won't be a problem if we use S3 Turbo with StreamDiffusion. Like as a mixed model.
I'm not sure I get your question, but we basically can incorporate LoRa like freely. Yeah.
Oh yeah, like when I went through the code, right? So diffusers were being used, Hugging-based diffusers were being used, right?
Yeah.
So and there either we can use LCM checkpoint or either we can use LCM LoRa, right? So the pipeline was loaded with LoRa weights, right?
Yes.
So before that, for the whole pipeline, we can directly utilize the checkpoint for SD Turbo.
Right. Yeah.
That was.
Yeah. We can utilize the checkpoint from the diffusers.
Awesome.
Great.
Any other questions from audience in Discord or here? Looking like no. Well, this was so amazing. I love to see the improvements in temporal inconsistency. That was very exciting for me. The one thing I was like, oh, I know what that is. No, I'm kidding. So thank you so much for joining. And maybe we can do a part 2 in the future, depending as things continue to advance. Rick, anything from you before we sign off?
Yeah, I just wanted to say as well, like, thank you so much for your great presentation. I'm looking forward working with you guys, with the engineering team, trying to get what you built into ComfyUI, really showing it to the world. And then I think we will contact you about it. We will first test out some things ourselves, build it, and then I already have a really good feeling of where we can start. First start with StreamDiffusion, then look at Stream V2V, look at the FPSs, look at the quality and FPS trade-offs, and then if you're ready with Stream V version 2, we have enough knowledge to quickly implement it as well in ComfyUI. Very excited about it. Thank you so much for your time, and talk soon.
Thank you. Thank you.
All right. Bye, everyone.
Thank you.